Hi everyone, I am Dr. R. Bhaskaran, Associate Professor, Department of Biotechnology, Kamraj College in Technology, Virudhunagar. Today we are going to see about the topic of one-dimensional steady-state heat conduction. So what is conduction? Conduction is nothing but the transfer of heat energy from the one place to another place. Generally the heat should be transferred from the high temperature to the low temperature. What is the basic law for conduction? It is a Fourier's law. We already known that. What is Fourier's law? It is the rate of heat transfer per unit area is directly proportional to the temperature gradient. So based upon the Fourier's law, the heat should be transferred from the one place to another place by the conduction. Here we are going to see about the how the heat should be transferred in a various surfaces. Example, the one-dimensional steady-state heat conduction in parallel flow, and then one-dimensional steady-state heat conduction in hollow cylinder, and one-dimensional heat flow through the composite cylinder. So these are the topic today we are going to see. So it is the Fourier's law of heat conduction. It is nothing but the rate of heat flow per unit area through the homogeneous solid is directly proportional to the temperature gradient. Here the Q is nothing but rate of heat transfer, A is the area, dt by dx is the temperature gradient. So Q is equal to minus of Ka into dt by dx, where K is the thermal conductivity of the material. It is called the proportionality constant value. First we are going to see about the how the heat should be transferred in the plane wall. Okay. So let us consider a plane wall. In this plane wall, the thickness of the plane wall is 0 to L. So the inlet temperature of the plane wall is T1, the outlet temperature of the plane wall is T2. So that first the temperature T1 is high, the T2 is low. So it is mainly used for the building construction. So mainly in the during winter season, the heat should be continuously lost due to the surrounding through the plane wall. So that it is observed that the heat transfer through the wall in perpendicular direction of the wall surfaces, there is no significant heat transfer has to be takes place. So it is mainly based upon the Fourier's law, that is the heat conduction through the plane wall can be modeled to the one-dimensional steady state by the using Fourier's law. What is Fourier's law? We know that Q is equal to minus Ka and dt by dx. In the plane wall, the thickness is 0 to L, and then the temperature is the T1 inlet temperature, T2 is the outlet temperature. So we have to integrate the dx. Dx is nothing but thickness. We have to integrate the dx to 0 to L, and then K is the thermal conductivity, A is the area, dt is the difference in temperature. Here the inlet temperature is T1, outlet temperature is T2. So we have to integrate with respect to T1 to T2. Here the thickness is 0 to L. So we have to integrate to 0 to L. So Q is the rate of heat transfer. We can integrate the dx, we can get the L, and minus of K into A. So dt is the T1, T2 minus of T1. Okay. So the whole equation comes Q is equal to my Ka into T1 minus of T2. So we can get the rate of heat transfer. Q is equal to interchange the equation. We can get Ka divided by L, T1 minus T2. K is the thermal conductivity, A is equal to area, L is equal to thickness, and then T1 is the inlet temperature, T2 is the outlet temperature. It is the rate of heat transfer through the plane wall. That is the Q is equal to the rate of heat transfer by conduction through the plane wall is proportional to the average thermal conductivity of wall and the temperature differences and inversely proportional to the wall thickness. So it is a final form of the rate of heat transfer through the plane wall. Next one we are going to see about the heat transfer through the hollow cylinder. It is mainly used for pipe. Okay. So let us consider the hollow cylinder. The thickness of the cylinder is R1, that is inlet radius is R1, outlet radius is R2. So inlet radius is R1 and outlet radius is R2, then T1 is the inlet temperature, whereas the T2 is the outlet temperature, and K is the thermal conductivity of the hollow cylinder. So we already known that the law of heat conduction by the Fourier's law, Q is equal to minus Ka into dt by dr. Here we can put as dr. Dr is the radius, hollow cylinder, we can mention as a radius. So we can put as the dr value. Instead of dx, we can put as dr value. So it is a hollow cylinder. The area of the cylinder is 2 pi RL. So we can substitute the Ka for 2 pi RL value. So the equation becomes Q is equal to minus K area 2 pi RL into dt by dr. So we can interchange the equation. So Q is equal to dr by r minus equal to minus of Ka into 2 pi r into dt. We integrate the dr by r with respect to r1 r2 because r1 is the inner radius and then r2 is the outer radius, whereas the T1 is the inlet temperature, T2 is the outlet temperature. So, we have to integrate with the T1 T2 and then r1 r2. In case left side we can integrate with the r1 r2, we can get the ln of r2 by r1, whereas here we can integrate with respect to temperature T1 T2. So, dt become T2 minus of T1. So, here minus. So, we can interchange the equation, it is plus. So, T1 minus of T2. So, the final form, the magnitude of the rate of heat transfer conduction through the hollow cylinder is Q is equal to 2 pi KL T1 minus T2 in ln of R2 by R1. It is the final form of the rate of heat transfer through the hollow cylinder. Next one is the heat transfer conduction through the composite structure. First we know the what is meant by composite structure. So, the composite structure is nothing but the arrangement of different material with have a different thermal properties like thermal conductivity. Different thermal conductivity of the materials are joined together to form the composite structure. So, how the heat should be transferred or through the conduction in the composite wall. So, it is the composite structure. Here L1 first part of the composite structure, this one, second one and third one. First one you have a thickness of L1, second one you have a thickness of L2 and third one has thickness of L3. The inlet temperature of the first structure is the T1, outlet temperature of the first temperature T2, whereas the inlet temperature of the second portion is T2, outlet temperature second portion is T3. The inlet temperature of third layer is T3, then outlet temperature of third layer is T4. So, it is a composite structure, it has a different thermal conductivity and also different materials are joined together. So, we can first write the Fourier's law of heat conduction, that is Q is equal to K1, K1 represents the thermal conductivity of the first layer and A is the area and T1 minus T2, because the T1 is the inlet temperature first layer, T2 is the outlet temperature first layer. So, L1 is the thickness of the first layer. Similar way for second layer, it is the K2 is thermal conductivity second layer, area is the common and then T2 is the inlet temperature of the second layer, T3 is the outlet temperature third layer and L2 is the thickness of the second layer. Similar way for third layer, K3 is the thermal conductivity of third layer and T3 is the inlet temperature of the third layer, T4 is the outlet temperature of third layer and then L3 is the thickness of the third layer. We can combine this equation, we can return as T1 minus T2 is equal to Q by A into L1 divided by K1. So, T2 minus of T3 is a Q by A into L2 by K2. T3 minus of T4 is a Q by A into L3 by K3. So, we can join this equation, finally we can get T1 minus of T4 equal to Q by A. So, T1 is the inlet temperature first layer, T4 is the outlet temperature third layer equal to Q by A. Q is equal to rate of heat transfer, A is equal to area of the heat rate is common, then L1 divided by K1 plus L2 divided by K2 and then L3 divided by K3. It is the rate of heat transfer through the composite structure. So, the rearrange the above equation, finally we can get that rate of heat transfer Q is equal to A into T1 minus T4 divided by L1 by K1 plus L2 by K2 plus L3 divided by K3. This is the rate of heat transfer through the composite wall. Thank you.